I have a very pleasant surprise for you all today. And the surprise is that we are just going to talk about today about the derivatives of the trigonometric functions. Aren't you excited now for it?
Cool, cool.
You couldn't wait for it, I think, huh? Okay. And just please have something to take a note, because the first period of the class is going to be the most important, I should say, lectures we're just going to have before the year ends. It's going to be very crucial. Then please make sure you take notes, ask questions as much as you can, because this single period is going to be the most important period of your whole career for the calculus before we just go for the holidays. Okay. Where are the others? I'm missing Billy. Where's Billy? He didn't show up yesterday. Okay. Guys, by the way, any questions about the test, the quiz which you had yesterday? No? The second period, before the second period ends, I'm just going to do that on the board, and I just give you back the results which you had from yesterday. During the break, I'm just going to give you back the results, and do that on the board in case if you have some kind of questions about it. Okay. Just the question is that if you remember about the derivatives, we talked so much about that. We just started, I should say, from the first week of the lessons. We talked about the functions, not in the function space, a function which represents a kind of a machine to take an input and produce an output. Then we talked about the concepts of the limit, that what the limit is and why we do use it. Sometimes you just want to assess the behavior of a function at the proximity of a number which it may not belong to its domain. Just want to evaluate how the function may respond back to you. And we use the concepts of the limit to talk about, I should say, the derivative of the function, which essentially we had two interpretations for it, two descriptions. The first description was that the concepts of the limit. Hi Alan, how are you? The first concept was that the first description of the derivative was that the derivative gives you a rate of a change of a function when you move along, I should say, an interval on its domain, or the geometric representation and interpretation or description of a derivative was that it gives you the slope of a tangent to a function at the point which it belongs to its domain. Are you so far with me? That was essentially 2 minutes review of what all we did since 3 weeks ago. And if you remember, we just, in order to define the derivatives of a single variable function, we talked about this one, that the d over dx of a function, f of x, essentially is nothing than the limit of f of x plus h minus f of h when h goes to 0. Previously, for the h, we talked about the delta x, but now I just put it back to h, anything it can be. It's a dummy variable. Then it doesn't matter, essentially. Oh, sorry, it should be f of x. That's right, because if you remember from the geometric representation, we said that if it's going to be the function which just starts from the x, then we take a distance of h, then we are at x plus h, then we had here f of x, then we had here f of x plus h. Essentially, that's what we did 2 weeks ago, and we said that the slope at this point is going to be f of x plus h minus f of x divided by what? Divided by this minus this, which it gives you what? H. Super. And because we said that the concepts of the calculus is that to make these steps which you take to distance yourself from the origin is going to be too small, we said that we just push h to go to 0, the width becomes as small as possible. Then that was where we used the concept the useful concepts of the limit of a function. And that's what we did, I should say, the last term, the last week. It was a kind of a review, and I'm just gonna just erase it. I just wanted to mean that this formula, where did we get that from? That's essentially that thing which I did it on the board from week number 2. And now, in this formula, you have noticed so far, we were able to use it as a kind of a master equation. You can get any kind of a formula of a derivative simply by using that equation. Simply by using that equation. And now the question is that if we have a function which is periodic, it means that at any certain intervals, the function repeats itself, like the sine function, y equal to sine of x. You know, that's the basic kind of a trigonometric function. The function repeats itself at every 2 pi interval. You see the exact copy of the function is there. It's as if you have your picture, you paste your picture on the wall after each 1 meter. It means that you are doing a kind of a periodic, I should say, behavior. For this function, I just want to ask you, please take a couple of seconds, try to use this formula and guess what is going to be the derivative of that function if we use this formula. And now your f of x, I can just simply, instead of the y, instead of I just make it very much easier to figure this out, put f of x equals to sine of the x. I give you 2 or 5 minutes to try to wrestle with it, try to grapple with it, and see if we can just get the derivative of the function by using simply this formula. I'm sure that you have your pencil, piece of paper, and now please give it to yourself a try. And in the meantime, BK is just going to sit himself. Really, the task is now to find the derivative of this function using that equation. Okay, guys, let's do that together then. Maybe it's going to be much faster. I'm just going to ask you to help me, like Michael, to just... Yeah? You're ready, Michael?
Yeah.
Yeah, okay. Let's get this one. What I'm looking for this one. I say that what is the derivative of sine of x? What does it mean? As you know that so far, by this notation, what do I mean? I mean that I'm looking to evaluate how the function sine of the x changes or responds back to you when you make small changes with respect to the x. And remember, I have x there as a single variable, and I have d of x as a single variable. This is very crucial when you're just looking at the function. And you will see in less than 1 minute why I just emphasized on that. I'm going to find this one. But how can I do that? I'm just going to use this master formula. You cannot do the magic to find it. You have to always find this master formula. What I do, I say, okay, I'm just going to find this limit. The limit of, what is the f here for me? This is sine. I put what? Sine of x plus h minus f of x. What is f of x? Sine x. Minus sine x over h. And there is something missing, which is the head, which is going to be how the limit is going to move. And you see that you're taking h, pushing it to 0, based on the definition. Okay, for this one, I didn't do anything much, except I plugged the function itself into the basic definition of a derivative. Nothing, I didn't do anything yet. What is going to be the next step, you think? What the next step is going to be then? The next step. Any ideas?
You define that formula.
That's so true. I can just use this formula. Look at this expression. I have sine x plus h. Does it remind you of anything? That we said that before? Sine alpha plus beta. As an identity, we know that it's going to be sine alpha cosine beta. plus cosine alpha sine beta. Still, I haven't done anything. That's an identity which I remembered from 20 years ago. And I hope you remember it from a year ago. That's its identity. I'm just going to use this identity for this expression, except the alpha is going to be x, beta is going to be the h. Huh? Then I have the limit. Okay, of what? I expand this one. How do you expand this? Please everyone say something and help me to write. Say something. What do I have to write? Expand this one.
Sine x
Sine x.
cosine h
Okay.
plus cosine x
Okay.
sine h
Sine h over h. H goes to 0. But there is something wrong. There is something wrong. What is wrong there?
minus
Minus sine x. I have to also put that there. Minus sine x. You see? So far, I haven't used so much brain because I plugged the function into the formula and I use that identity. Guys, please do not talk during the lectures. Thanks. And I didn't do much except the formula and the identity. Okay, what's going to happen next? Now the story starts from here. If you had Elvis 2 years so far, you have to borrow 4. Our real job starts from right there. Yes, Alan? This is going to be the true job here. What I'm going to do is that I'm just going to rearrange this expression. How come? Look at this. This is going to be the plan. I have sine x here. And I also have sine x there. Huh? Then as a result, I just try to combine these two expressions together. And it becomes like what? It becomes limit of sine x cosine of h minus sine x. I have that term left plus cosine x sine h, all the terms over h goes to 0. Huh? So far so good? And what do I do later is that now I see these sine x are similar in these two expressions. Then I do what? I just factor them out. I say, what? Everyone can see this here if I write it here? Jake and Lee, you're at the back. You can see this if I write here? Yes? Okay. Then what do? I say still have the limit. This part is very crucial. I take the factor of the sine x. Let me write it in green. Sine x. What I'm left with? I'm left with cosine of the h minus what? Minus 1. So true. Minus 1. Because I'm factoring between these two terms just the term which is common, which is sine of the h. Then from the first term, I have cosine of the h. From the second term, I have minus 1. Plus cosine x sine h. And you see all of these terms divided by the h, and h goes to 0. So far everyone is with me? Okay. And now, the next step, things are getting to its own shape. Things are getting, I should say, more concrete. I'm right now there, and I see I have two expressions. And both of them are divided by the h. You remember from the very basic algebra that a plus b divided by h, a and b, there are two expressions. Essentially, it's like that. You divide each term over h. It means that you get right a over h plus b over h. Is it acceptable for you or not? If this is acceptable, then the thing which I do, I just decompose this final expression into a limit of two functions. Limit of two functions. One function is going to be the left, one function the right of the plus sign. Huh? Then I just take the things up. I'm just going to write it up right now there. Then it becomes, I write it again as d dx of the function which is sine of the x equals to the first expression is going to be the limit of sine x, then cosine h minus 1 over h, because this sine x is multiplying this here, I can just take this outside and cosine h minus 1 over h remains where it is. I am careful that h still is pushing towards 0. I have a plus sign. I take plus, and I take the limit of the second expression. And I say that the limit of what? Cosine of the x, let me write cosine in green, of what? Sine h over h. Again, h is pulling towards 0. If you are surprised, and if you are not happy that why the thing happens like that, I'm just going to remind you this very basic identity which we had for the limit. We said that, if you remember from previous sessions, limit of two functions, f of x plus or minus g of x, when x goes to 0 or pushes towards 0, is that you can decompose these expressions to two limits. It becomes the limit of the first function. X can go to anywhere. Sorry, a. A can be any real or complex number. Plus or minus the limit of g of x. I believe x goes to 0. It was an identity which we learned previously, that if you have the limit of a function which there are plus or minus between them, you can simply decompose them to two individual limits. And that's what I use this identity to take this one from there to write it like that. I used Elvis' expertise on pulling the curtain down, and it proved very effective. I didn't do much except using this identity to take it out. Billy, we are just doing this one. The task is this. The function is sine of the x. We are using the Manser formula of the derivative to find the derivative of the sine of the x. I put sine of the x into the function, and I'm just following all the way there. Okay, any questions so far? No, everybody's fine? Nothing is bizarre so far happening, huh? Yes, Alan, you're fine. Michael, Tony,
Yeah.
Elvis, PK, Holden, Billy. You just arrived, I give you some time to digest what's happening. Lee and Jake. Everyone's fine, huh? Okay. And now, the sweetest part of this is gonna start right now. Imagine that's an apple pie. You are gonna take a sweet apple pie now. And what is that? I'm gonna start continue from this. I'm gonna continue from that. And to continue from that, what do I have to do? Okay. Guys, look at that. It is BK and Elvis. It's very crucial to listen. Listen, this part is very crucial. Don't miss it. Look at this expression. I have the limit. Look at the first expression. The limit of the first expression is limit of the sine of the x of the cosine of the h minus 1 over h. Alan, listen, then you have time to write it because this one is crucial. Look at the first expression. Forget about the right side, just the left side. For this limit, look at that. What do you think of it? I have sine of the x in green, cosine of the h minus 1 over h. What does it mean? Look at that. It means that you're pushing the h towards 0, and this expression, they are a function of the h. But the sine of the x, which is the multiplication to the whole term, look at that, the sine of the x is multiplied to the whole term, has no h dependency. It's like what? It's like you come to say, okay, I'm just going to find this limit. I'm going to find the limit of f of x. Look at the signs. It's very crucial. X goes to any number you are familiar with this notation. Limit of f of x, x goes to a. You see that x goes to a, and the function is a function of the x. But imagine that I have something like alpha or c anything. Multiply to that, and it has no dependency on the x. You cannot, if you take the alpha, open the bag, which is the alpha, you take a look inside, you see no x inside. It has no x. Because x goes into a, but the alpha is completely out of, I should say, the market, no dependency on the x. It means what? It means that you can write this one, limit of f of x, still x is pushing towards a, but you can take alpha outside. You can take alpha outside of the limit. You had something similar with the derivatives. You remember the derivative, you can take constant outside of the derivative operator. This thing is very natural. It's very crucial, and it's very easy to remember. Okay, and now what's gonna happen next? What's gonna happen next is this. I'm gonna use this identity for this expression. Look at here, cosine h minus 1 over h, it's a function of the h. And you will see the h is going to 0, and when you look at the sine of the x, it's the back. You open the sine of the x, you see no h. It means that that's right, Tony. You can just push the sine outside. Then it becomes what?
Sine.
So true. Then you can simplify that to sine x, the limit of cosine h minus 1 over h. H is pushing towards 0 plus the same thing over there, the same expression. You see, it's very easy to find this. You see h is going towards 0. And you have sine h over the h. And you have cosine of the x, which cosine of the x is multiplied to that expression, like the one which I have there. It's multiplication. And the cosine of h has no dependency on the h. Then it means that you take the cosine of the x, like the ball, shoot it outside. It becomes like what? Plus cosine of the x, the limit of sine h over h. H goes to 0. Is it so far acceptable for you? Huh? Yeah. You see, still we haven't done anything crazy. It is still some basic rules of the limits and the derivatives which we have learned. Isn't that beautiful, guys? Huh? Elvis likes it very much. Any questions so far? Any question about anything so far? No? Alan? Michael?
No.
Tony? Did you got it, Billy, so far? What's happening? If you have any questions, do the way I explained it to you from the beginning. Then. Holden? No problem. No problem. Elvis? BK? Jake? Lee? You are fine, huh? Okay. And now, let's see. We aren't yet done. We aren't yet done because as you will see, I give you a couple of minutes to write, then I continue myself. Okay, guys. Now, if everyone is done writing, I'm going to continue from this stage. Okay. What's going to happen now? Look at that. We just started from here. We had a big question in mind. What is the derivative or the rate of change of the sine of the x? We had to use this formula to answer that question. We ended up with these two limits. It's so funny. We had one limit in the basic definition, and now we ended up in two limits. One limit gave birth to the another one. And now then we have to find two limits. For the first limit, which is this one, there are two ways to measure it. Jake, are you okay? You want to go outside for wash your face, take a break, coffee, do some muscle building outside the gym? No gym? Okay. Look at this one. For the first expression, I'm just going to give you a hint. In future, we are going to prove it when we learn more about the series, an expansion of the series, which is called Maclaurin and Taylor series. But before we get there, you can always think of that. The sign, let me write it I'm just going to use this sign of the board for the notes. Let me use this sign. We say that the sign of an angle, I call that angle as alpha. When alpha is going towards 0, it means that the alpha is very small. Alpha is very small. You can approximate it as alpha itself. And there is one more term, plus 1 over 3 alpha cubed, 3 factorial. We're not going to deal with this. We're only going to deal with that fact, that only for sine alpha, when alpha goes to 0, it means that alpha is extremely small. You can approximate it as alpha itself. I'm going to show that to you in the other room. I'm going to give you, when we have the projector, I'm just going to plot two functions, sine alpha, and for example, I'm going to plot two functions, like y equals to sine x, and also y equals to x. It's going to be, the plot is going to go like this. You can try it yourself when you have Desmos. The sine x is going to look like that. It's a plot of the sine of the x. And when we plot y equals to x, I'm just going to plot it by a different color. With a different color, it's going to be y equals to x.
This is tangent line.
That's so true. When you look, when x is going to go to 0, then x is going to go to 0. When it means that the x is too small, you see that the sine function is like y equals to x. You can prove it yourself. You can show that on the Desmos. Plot these two functions. You maximize the view. You see that when x is too small, sine x is like y equal to x. Except when x is small. When x gets large, you see these two are crazily different. Okay. I'm going to use that identity, that thing which I know as an approximation, to find the first limit. The second limit is social lining. I have this term, I have plus, I have cosine of the x because I don't have anything to do with it. Cosine of the x. Guys, limit of sine h over h when h goes to 0, based on the approximation which we learned. What is that going to be? Who can guess? Find this limit. I have the cosine of the x. It doesn't have to do anything with the h. Then it is completely outside. We shoot it and kick it outside. Only we have with this term. Limit of the sine h over h when h goes to 0. Use this approximation and see what value you get for that limit.
1.
You get 1?
Not sure.
Not sure. Who knows?
0.
You get 0. We have two answers now. 1 and 0. What else? Close your eyes. Holden wants to answer. Holden, what do you get for this limit? Use this approximation. Talk to someone next to you. Share the idea. Alan, what about you? Michael, Billy, Lee, Jake, Holden, BK, Elvis, Michael, Alan. We have two answers, 1 or 0. 1, 0. We have 2, 1, 1, 0.
1.
Jake also goes with 1. Who else says 1? Holden. Billy also says 1? 1? Most of the people says, Michael, how about you?
I don't know.
Okay, then now Michael is going to help me to find the answer. We have lots of answers for 1 and some answers for 0. Let's see which one is that. Michael is going to help me. Elvis, how about you? Any answer? Guess?
1.
1. Also, we have 1. How is that going to work? Guys, look. I have the limit. I know that the sine h, when h goes to 0, when h is extremely small, you saw the plot. It becomes like the h itself. Then I have the sine of the, becomes h. At the denominator, I have still h. Then h also goes what? Goes to 0. Which essentially is what? H over h is 1. The limit of a constant when h goes to 0 becomes what? Becomes 1 itself. This is essentially this one. The limit of a constant when x goes to any number. What is the result for it? Yes, Michael. The limit of a constant number when the variable x goes to a. It's like that. Y x and y is constant, y equals to 5, for example. When x goes to 10, what is the limit?
5.
Still 5. That's so whenever you just go to the 10 or any number, you cut the graph on y equals to 5. Huh? Then it becomes 5 or c as a constant. Huh? Then as a result, it becomes plus. I have cosine x times 1. Becomes what? Cosine x itself. Because the limit of h over h becomes the limit of 1 when h goes to 0. This is exactly like this one, as Michael said. It still becomes 1. Cosine x times 1, which is cosine of the x. And now we got the value for the first limit. Any questions? We only did this part so far. The cosine of limit sine h over h. And we use this identity and also this identity to find the value of cosine x.
So you just take it out sine.
That's right.
Okay.
You just for the sine, you take h outside, h over h becomes 1.
Okay.
Then the limit of 1 when h goes to 0 becomes always 1. Like the one which Michael showed out on that graph. It was 5 instead of 1. It always, the limit of a constant, when x goes to any number, becomes a constant itself. Michael, you look surprised.
Where is the sine?
Where's the sign? You mean this one?
No, that.
That's the, I use this identity Then when sine alpha is too small, sine it becomes alpha itself.
Oh.
Then I remove the sine from it. Then I use that approximation from this. This is that approximation. Huh? Okay. Any questions, guys? And now, we are left only, we had two limits, we measured one limit. We have still one limit left. And this is this limit. The sun, I give you some time to write. Isn't that beautiful, guys? Calculus. Everything is systematic. You follow the things which you learned before, and you get the answer at the end. Okay. And now, what I'm going to do, guys, look at that. I have a value to fill out for this part. Because this part is the value for this limit. The sine of the x, the limit of that function. Huh? What I'm going to do is that the sine of the x, you keep it outside as a football. You keep it outside, you keep it still here. Sine of the x. Huh? But the thing which you have in there, the limit of cosine of the h minus 1 over h when h goes to 0. I give you 1 minute. Guess what is the value of that limit?
0.
I get one answer for 0. Cosine of the h minus 1 over h when h goes to 0. I plug in 0, for example, there. When you have a limit, the most logical thing which you do is that you plug 0 into the value of the variable. Cosine of the h becomes how much? Cosine of 0 becomes how much?
1.
Becomes 1. 1 minus 1? 0. Over 0. Oh my goodness. 0 over 0. You have to run away. No, oh my god, no. 0 over 0, guys. I told you before, 0 over 0, it means that you have to run away from it. It's awful. Whenever you see 0 over 0, you have to, Michael, what? Run away as fast as you can. It's gonna bite you. Huh? Like a dog, it's gonna bite you. And you don't want to be beaten. Huh? Then how do it become 0, Paul? How does it become 0 then? Because it becomes 0 over 0. And it's unacceptable. It's like a dog who just wants to bite you. You have to run away from it. Then how is that possible? That it becomes 1 or 0. Then it means that we have to find a better solution for it. Who knows how to find the value of this limit?
You got first times that, then divided by.
Huh?
You got first times h, then divided by.
Say that again, please, Lara. I have some problem with my ear.
First you got times h.
First I do times h.
Yeah, then no answer and divided by.
If I times it by the h, then it becomes what? Then it becomes limit of cosine of the h minus 1, h goes to 0, then becomes 0, then multiply that to the h when h still goes to 0, becomes 0 times 0. 0 times 0 is like 0 divided by 0. If it's the dog who bites you, this is the sister of that dog. It's gonna also bite you. You have to run away from it. 0 over 0, 0 times 0, not acceptable. I suggest one solution, Fred. Now let's do that together. I'm going to write it here. I'm going to write it.
Multiply cosine h divided.
You are so close. Billy said that, multiply that to cosine h divided by cosine h. It's so close, but with some modification. Cosine h minus 1 times h. I'm going to multiply that to the conjugate.
Cosine h plus 1.
That's right. Cosine h plus 1, this is a conjugate of this, times the same thing because I don't want to change the value of my fraction. Cosine h plus 1. Lee, are you enjoying the calculus? Isn't that funny? Isn't that beautiful? You're enjoying it? Super. Then h goes to what? 0. These are the workings. These are not the, it doesn't relate to this side. These are the workings. I'm just going to find the value of that limit, plugging it in there, into the rectangle, multiply the sign, then I'm done. And that's a strategy which Billy was so close to suggesting. Multiply both sides. Essentially, this fraction becomes 1, and it seems as if nothing has happened. How much do you get, Fred? You get the limit. I'm going to multiply this to this. If you multiply this to this, how much you get on the numerator? Here, please do it yourself. Do the limit yourself. Do the limit continue yourself. Continue this part of the limit yourself, then I do that on the board.
Sorry. Why? 这个后面写的草书。后面结果是啥？算哪个呀？算那个cosine h减1。这个咋算？不还是最后不还是得1吗？不是吗？
Any answer for it yet? It's a very good exercise, I should say, for the concepts of the limits. It's not an easy limit. Then that's why it's good that you try it first yourself. Okay, I'm just going to do that. You help me. Anybody just got the answer yet? No one yet? Then you help me to find the answer first. Okay, if I just want to find the limit, I know the first thing which I have to do, I have to find what value do I get from inside the stomach of that limit. It means that I have to multiply numerator to numerator, denominator to denominator. From the denominator, what do I get? I get h times cosine h plus 1. Numerator gives what? Gives you cosine squared of the h minus 1 to the power 2. H goes to 0. Yes? What is that essentially? Isn't it still safe if I plug the value of h goes to 0? Because what was the initial problem, Lee? The initial problem, Lee, was that this limit, this one, is a bad limit. Because if you put h equals to 0, it gives you 0 over 0. In order to just stay away from a dog which is going to bite you, Wheeler suggested that we can just multiply those two, for example, the cosine h plus 1, the cosine h plus 1. We get this to this simplified version. And now we took one step. Yes, Alan? And that step is that, okay, is it now safe to plug h equal to 0 to this final expression? What happens? If I plug h equals to 0, what do I get? I get cosine of 0 becomes how much? Yes, Olga? How much do you get cosine of 0? I'm going to plug 0 there. 1. 1 to the power of 2 becomes 1. Again, we have 1 minus 1 becomes 0 divided by h again 0. H goes to the 0. Becomes 1. And h, that's right. Then here, h goes to 0. Cosine of the h becomes 1 again. Becomes 1 plus 1 becomes 2. 2 times 0 becomes 0. Again, you have 0 over 0. Disgusting. Disgusting.
Oh. Break.
You need a break?
可以不 break， 但是
We are going to get done. We are going to be done in 2 minutes. We are going to be done in 2 minutes.
我不会限制了。
You see, guys, before we finish it, it takes only 2 minutes to finish this limit. But how to get the problem exists? Any other suggestion, Fred? The suggestion is that, for example, it's not easy to find that suggestion. I couldn't probably do that myself before looking for the book. But is that, guys, do you remember this formula that the cosine squared of the x plus sine squared of the x becomes 1? This identity. The most important identity is trigonometry. Then as a result, cosine squared of the h minus 1 becomes how much if you just want to use this one? Becomes, you take this one, in this sign becomes minus sine squared of the h over the same thing. H, still I have the limit, h times cosine h plus 1, h goes to 0. This, everybody can see that, or is it too small, the font? Everyone can see that? Yeah? Lee and Jake, you're at the back. You can see that? Okay. It becomes the limit of minus. Let me just put the limit with the limit. H goes to 0. Okay. And now, as a next step, I'm going to write this, then I share the result with you. Why did I write that like that? Guys, Jake, please don't talk. Please all listen. That's the final touch, the most important part of that limit. It seems as if you're baking a cake, and at the last seconds that the cake is ready in the oven, you don't eat it. We are at that part. You're just going to eat the cake. We're at this stage. I'm going to just put the minus sign outside of the limit, and I say minus the limit. Sine squared of the h, I'm just going to cut it in half. This is a strawberry cake. I'm going to cut it in half. 1/2 is going to be the sine of the h itself, divided to one part of the denominator, h, multiply, because this is multiplied to the limit of h, sorry,
Sine H.
that's right, sine h, the second half of that strawberry cake divided by whatever is left at the denominator. What is that?
Cosine H. Plus 1.
Plus 1. And in all of them, h goes to 0, h goes to 0. Huh? Now the strawberry cake is almost ready for you. And now, look at this. Again, we ask ourselves at that stage, is it now safe to eat the cake? Are we going to avoid 0 over 0 or not? I plug 0 to this first limit. How much do I get? 1. Yes, Tony, because we use the same thing.
Yeah.
H is going to be too small for the sign.
Oh yeah, 1.
When you take it outside, then you have limit of h over h when h goes to 0. Becomes, sorry, I'm at the very bottom, I hope everyone can see that. Becomes minus 1, the first limit. Multiply, okay, we take a breath. We are not 0 over 0 for the first limit. The second limit is the sine h cosine h plus 1 when h goes to 0. How much is the value of the limit? 2. Holden says 2. Let's see. Sine of the h goes to 0. How much is that?
0.
0 over cosine h plus 1, h goes to 0. Cosine of 0 becomes 1. 1 plus 1, 2. Is it acceptable? We have essentially 0 over 2. Oh, it passed the problem. The cake tastes very delicious now, guys. Because 0 over 2 is not 0 over 0. 0 over 2 is how much, Tony? 0. We have then what? We have minus 1 from the first limit times 0 from the second limit. How much is that? 0. Super valid. Then I take the value of the 0, I take it from the oven and put it back on the table to eat it. And now look at that, Alan. Sine x times 0 becomes how much? 0 plus cosine of the h becomes how much?
1 cosine.
Who says 1?
No.
Yes, Jake, you have a question?
No.
No. Then sine x times 0 becomes 0 plus cosine x becomes cosine x. And bon appetit, guys. The cake is ready for you to eat. And we proved that the derivative of the sine of the x becomes what, Alan? Cosine of the x. Then as a result, take this lesson for yourself, that d over dx of sine x equals cosine x. Yes, PK? Huh? And that's it. That's essentially what we proved it here. I just went with the red on the board. That's how we proved. Use the master equation to get to this point that the derivative of the sine of the x becomes cosine of the x. And we used part of our brain to find these limits. And it was a very good exercise to use the limits concepts to take you there. Yes, Alan, do you have questions? Everyone is fine? Alan, are you okay? No questions? Michael? Questions? Tony? Questions? Elvis? Questions? PK? Questions?
No.
Alden? Billy? Lee? Jake? Everyone is fine? Then please enjoy your break. Don't forget to take some of the strawberry cake which you made it yourself.